Hello, Professor. This is Group 1. My name is Lin Wenxin. Today, we are going to present our final project, Agentic ECG HRV Baseline Evaluation System. Our focus is on ECG-based HRV analysis and how an agent-style orchestration system can reduce errors caused by fixed thresholds and activity-related bias. This is our outline. Today, we are going to talk about problem and motivation, system architecture, demo and result, challenges and lesson learned, conclusion, and team contribution. First, let's take a look at the personalization gap in healthcare. In physiological monitoring, we often rely on fixed clinical thresholds. However, this creates a serious personalization gap because normal heart rate variability differs significantly across individuals. Another issue is activity state bias. HRV patterns during rest and active motion are fundamentally different, yet many systems treat them the same. As a result, technicians must manually review large amounts of ECG data that are automatically rejected, which creates a heavy operational burden. Next, our motivation, agentic solution. To address these problems, we propose an agentic system solution. Instead of using a single static role, the agent manages contexts such as rest versus active conditions and applies state-aware validation logic. This goal is not to replace clinicians, but to autonomously filter out unreliable segments so that only meaningful physiological data requires human attention.
Hello, Professor. I'm Zhu Yanjie. Today, I will walk through our system's internal architecture and how we achieve high-precision personalization. Here, as you can see, this diagram shows our HRV analysis agent workflow. Our system is built on an agentic orchestration model, which consists of three main components. First, the orchestrator. It serves as the brain of the system, managing the entire data lifecycle from injection to task scheduling. Second, the adaptive analyzer. This is where the agentic part really happens. Instead of using a fixed script, it evaluates the signal quality in real time to select the most suitable RPIC detection algorithm. Third, the quality validator. It acts as an autonomous gatekeeper. It verifies the extracted HRV metrics against our personalized distribution to ensure that only reliable data is passed into the final reports. In page 6, we discuss our personalized profile store. This is how we solve the personalization gap in healthcare. We use a file called baseline.json to maintain individualized psychological norms for every user. Our system tracks specific metrics like RMSSD, SDNN, and mean heart rates. And crucially, we separate this into different activity states, such as rest and active. By doing this, the agent learns each user's unique heart rate signature over time. This allows us to adjust validation threshold dynamically, which significantly reduces the need for manual review by clinical staff.
And using this pipeline, we were able to analyze 16 ECG records in a fully automatic batch process for most activities, especially in biking and static conditions that the system achieved high pass rate even when moderate noise was present. This indicates the personalized baseline are more robust than using fixed thresholds. However, there is one clear exception. For the rotate activity of the first sector, the pass rate drops to zero if we look at the raw ECG signal shown in the top right. We can see that the waveform is mostly flat, followed by suddenly extreme spikes and signal drops out. This pattern do not represent real heartbeats. Instead, they are motion artifacts caused by sensor instability during rotational movements. Because of the arc detection becomes unreliable as a result, the extracted HRV feature shown in the bottom right list display unrealistic trade and fall from outside the personalized baseline. Therefore, all analysis windows are correctly rejected. This is actually a desired outcome because it shows the agent can effectively prevent corrupt ECG data from being misinterpreted as a valid psychological information. One major challenge was balancing how much reasoning the agent performs with overall processing speed. We also found that consistent and standardized pre-processing is crucial for obtaining reliable HRV features. Most importantly, our results show that using an agentic baseline-driven approach helps reduce activity-related bias much more effectively than static systems. To conclude, our system demonstrates how personalized psychological baseline can effectively bridge the gap between raw ECG signal and reliable HRV interpretation. By applying adaptive rule-based validation, the agent reduced manual verification effort while maintaining interpretability. And this is our team contribution. Thank you for listening. Okay, next up is me, Lin Zhiyi, will demonstrate. I've already written the prompt, so can ask you directly. And our cover state is value preparation performed by calculate value. The state compute ECG and HRV related statistical quantity are required by later stages. And the stand state is the main agentic analysis executed by run analysis. The orchestrator coordinate ECG preprocessing repeat detection, HRV feature extraction, and data level evaluation using personalized psychological baseline. After the analysis, we use two visualization steps. The first, visualize raw ECG signal by condition, allow us to inspect signal quality. The second, visualize HRV feature distribution, helping interpret difference across individual and active states. And after the demo, the system will produce several key outputs. And the first is baseline JSON, store personal psychological baseline for each individual and condition, which are used for context-aware validation. And the second pass is pass rate. It summarizes Windows level pass and fault result and aggregated pass rate, indicating how reliable each ECG recording match its personalized baseline. And the generate ECG and HRV plots provide visual evidence to support the evaluation result and help explain why certain segments are accepted or rejected.